guys, making YouTube videos is harder than I thought it was going to be. I mean, the content is alright, but how the hell do you get these, the microphones need to be set up in the right place, and okay, so either I have the microphone too low and you can't hear me, or I have it too high and there's some bird in the garden three gardens away, chirping, and it's coming out, or you can hear me breathing heavily, or I suppose maybe you're meant to compress the audio afterwards or something. It's very annoying, or at least it's very confusing for me. So hi, Sinus Media here, and I'm going to do some tutorials that I'm calling how to build your first usable synthesizer in Pure Data, and it's this synthesizer, which is quite fun. And I'm going to kind of take you through all the stages in building this, and this is aimed at complete beginners, and hopefully you too, if you follow along, will be able to build something that you can actually use in your own music, either for making sounds, making drones, making little loops, sample those, or even with live performances, which is what Pure Data tends to be used for. Pure Data has been around for quite a while. It was actually written by the same guy that wrote Max, which is now incorporated into Ableton. It's Max for Live, but it's a free software, open source. You can download it, runs on all platforms. I use the Purr Data fork because I think the user interface is slightly nicer, and I will leave a link in the description of how you can get this. So let's just get started, and here I am in Purr Data, and I'm going to kind of try and I've recorded this several times, and every time I've made mistakes or I've kind of gone wrong halfway through, or you can just hear me breathing heavily or whatever, and so I'm just going to try and be more informal, and also it just got very long, so I'm not going to explain everything. If you're interested, then ask me some questions in the comments, but I start off with a horizontal slider. These are just a kind of standard input device, and we're going to set our main fundamental frequency. So I'm setting that between 0 and 1000 Hertz. We connect that to a sine wave oscillator. That's cool. So we put these boxes, these objects on the screen, and we define what they are by typing the name. The name of this is OSC with a little tilde on the end. The fact it's got a tilde on the end is a convenience for us. It tells us that this is an audio processing object. Pure Data has objects that are both audio processing or control processing objects. And audio processing objects have to be optimized to run fast, right? Because they're processing audio at 44,000 Hertz, 44,000 numbers a second. So just so we know which of these are the audio things, and we know that we can't plug an audio output into a non-audio input, they all have a tilde on the end. So that's just something to understand when you're reading or looking at these diagrams. We have an input box at the top. So these little grey boxes at the top are the inputs, and the grey box at the bottom of the object is the output. So that's our oscillator. It's getting a control signal from the slider that tells it how many hertz to play. We're now going to add a volume control so we don't deafen ourselves. Volume or amplification in Pure Data is simply multiplying all the numbers in the wave by, say, a constant or something else. This is programming languages in general tend to use the asterisk to mean multiply, and Pure Data is really just a programming language. So, but it's multiplying an audio frequency signal, so it's got the tilde on the end. So we're going to, let's say we multiplied everything in our signal by 0.5, then that would end up being half the volume, if that makes sense. So the final thing we're going to put here right now is the DAC, the digital to audio, or the digital analog converter. That basically is just our output jack. It's our audio output. You'll see when it's got two inputs because it's stereo, so we can join the same signal to both the left and the right channel here. It takes audio again, so it's called DAC with a tilde on the end. Finally, we're just going to put in one more horizontal slider to be our volume control. No, that's wrong. Go away. I'm not going to worry about mistakes. H slider here. Pull that down a bit to give us some more space. Take the out. This will be between 0 and 1 because the audio signal of the OSC is tracking out is between -1 and 1. Multiply that between any number between 0 and 1, and we will get. I mean, the volume control is mainly to diminish it. If we go above 1, it could get loud, too loud and clip. So that's our simplest circuit. Here I go into the main mode and I put this on, media audio on. Here's the frequency, so here's the volume going up, here's the frequency changing, and that's basically our simplest audio circuit we can make in Pure Data. Right, so now we're going to move on and we're going to make a very simple, actually I'm going to stop the video at this point because every time I try and record this all the way through, it always goes horribly wrong 30 minutes in. So I'm going to break this up into smaller chapters. So I'm going to pause and then I'll be back shortly. Okay, we're on chapter 2. So we've just built a simple oscillator. I'm going to do one extra thing here. I'm going to add a number box. These number boxes can be connected to control signals and they show numbers. So as you can see now, my frequency slider, as well as controlling the frequency, it's telling us what frequency the slider is sending to the oscillator. So we're going to now start building a simple FM voice, or frequency modulation voice. So the principle of frequency modulation is that we have a second oscillator that oscillates, changes the frequency of the first oscillator. So it's like this. I've got the oscillator playing and I now imagine that the mouse is not very responsive, but I'm wobbling that frequency of our main oscillator very fast, and that will change the character of the sound. So the main oscillator here in FM we tend to call the carrier, and the second oscillator that oscillates it, that changes, wobbles it, is called the modulator. It's a modulating thing. So to begin with, we'll break this connection here and we will do a simple test. We will add two more things. We'll add a second oscillator, which is our modulator. Now that's chucking out between -1 and 1. If you remember, the carrier oscillator is expecting hertz, a frequency in hertz, so we need to convert -1 to 1, but to the 0 to 1,000 effectively. So we'll just put one more thing in here where we will multiply it. Remember, it's an audio signal again, so we have the tilde on the end, and we will multiply the output of that first of the modulating oscillator here by 1,000 to feed in to the carrier, the main oscillator. We will also change this for a moment to just between 0 and 10, and we will connect this now to that. So let's put that down and put this up. And you can hear this oscillator, this carrier oscillator, is now its own frequency is going from 0 to 1,000 back again at the frequency, and that change is itself going at the frequency we've defined by the slider now. So if I put that up, it almost starts to turn into a tone in its own right. And if I put the range up to 1,000, you can really hear how it is becoming a different sort of a sound. And we could even put that up to 1,000. And it now becomes the equivalent of, it's now just controlling a pitch. You can hear it's not just a pure sine wave. These are both pure sine waves, these oscillators, but the quality is slightly different. So that's a basic frequency modulation, but of course that's not how frequency modulation is used in synthesis. So the first thing we're going to change is that typically we don't just oscillate the carrier all the way from 0 to 1,000 or whatever. We oscillate, we continue to give it a constant or a fundamental frequency, and we oscillate around that. So what we will do here is we will take that over to the right. We'll change this from, instead of being an oscillation of 1,000, we will oscillate this to be multiply that by 50. So now the signal coming from here is oscillating between minus 50 and plus 50. We will now create a new slider here, which is now going to be our fundamental frequency. And we will create a new object which adds those two together. So this is going to be this is a box that adds, just as this the asterisk tilde was a multiply, the plus tilde is addition, and we are going to add the signal that comes out of this slider, which of course we have set up to be between 0 and 1,000. That's our fundamental frequency, to the result of this oscillation, which is, I'm going to take that down to be 10, but it's basically something wobbling between minus 50 and plus 50. Now, for a reason I will not explain yet, we will take the output of that and connect that to the top left of this plus, and we'll take the output of this one and connect to the top right. But these are the two inputs that are being added together, and then we can take the result and feed that now to our carrier oscillator. So let's hear how this sounds now. We'll give it a frequency of about 500, and it's a pure thing. As we now increase the frequency of our modulating thing, as you can hear, it's now oscillating around that fundamental frequency. If we make the fundamental frequency lower, so it's almost like someone playing one of those musical saws or something like this. So yeah, so that's starting to be a more usable sound, but it's still not exactly the way we do this. So in practice, FM synthesis tends to use, you don't set you don't set the frequency of the modulation independently of the frequency of the carrier. You normally make it some sort of ratio to it, or function of it. Somebody seems to be banging in the background of this house. I hope that's not turning up on the microphone. So instead of giving that a fixed thing, what we will do is we will create yet another object, a multiply, and we will take the output of our fundamental frequency, and we will multiply it by we'll set this slider now to be, I found that up to about 4 is sufficient for this. So here is our top left, our slider is our fundamental frequency slider. Our top right is our, what I will call our ratio now. That's the ratio between the fundamental frequency and the modulator frequency. So it can go up to 4. In other words, the modulator could be going 4 times as fast as the fundamental, or it can go down to less, so it could be down at half or a quarter. Those two multiplied together feeds into the, we'll show you what that frequency actually is here. That will feed into this, and let's just put the amplitude of this up for a second to say 200. So now the frequency of the modulating oscillator could be, I mean, let's say the carrier frequency is about 500. The frequency of the modulator can be 1000 at that frequency, and it can be going between 200 and, so it can be between about 800 and 1400. So let's listen to this now. Okay, so why is that not doing what it's meant to be doing? Oh, alright. What I will need to explain to you at some point in the future, but I'm not going to explain quite yet, is the difference between this top left-hand input, which is what's called the hot input, and the top right-hand input, which is called the cold input. Effectively what it means is these boxes only recalculate when something new comes in on the hot input. So I've set this multiplication to be between this slider here and this slider here, top right, and you'll only hear the difference at this point when the slider at the top changes. Actually, I did just explain it, didn't I? But so if we listen to this tone now, and listen to how, particularly around the ratio of between 0.5 or 5, for example. Or 2. It's almost like there are 2 tones going along at the same time. And it almost has that kind of glassy, metallic type sound which we start to associate with FM synthesis. It's still not very like what we're used to yet. So I'm going to add one more thing here. Instead of this being a constant, I will also set this amplitude up to be controlled by a horizontal slider here. And we'll give that somewhere between 0 and 600. and we will take this down to here as well. And now we will play around a bit more. Let's put the amplitude up. As we put the amplitude up here, you can start to hear again glassy, slightly metallic, hollow sort of sounds that are, if we take the frequency, we take it down to 0, of course it goes away, but take it to almost 0, and you still hear how the... Right, I think I'm going to finish this here, and we'll see you in the next chapter. So, welcome back. That's our current state of our FM synthesis. It's a simple FM synthesis, but it's giving us a range of values, and we're going to now do two things. Firstly, a little bit of housekeeping. We will give these some labels. So we'll call this the pitch. We will call this because we're going to get a lot more sliders soon. So we'll call this the modulator, the ratio for the modulator, and we will call this the amplitude for the modulator, and we'll give that a number box so we see what we've got there. Finally, we'll call this the volume. Okay, so just we don't lose track of what we're working with here. Okay, so that gives us a range of FM tones, but I'm going to add one more feature to this that will really give us something extra to play with in terms of sound, and that's some simple wave shaping simply through clipping the signal. So what do we mean by clipping the signal? Imagine we've got our sine wave and it's going between -1 and +1. Well, we clip it by sort of setting a limit to the maximum and minimum values. We'll say we'll limit it to 0.7 and -0.7, and anything above that gets held at 0.7. What that does is it's like chopping the top off the mountain, or the bottom, the equivalent of the filling in the bottom of the trough. It gives you a horizontal, almost a square wave element to it. So and a square wave has a certain amount of harmonics. So it's a kind of distortion. It's a kind of makes for a grittier, dirtier sound, buzzier sound, because it's adding these extra harmonics. But if we want a rich sound for our synthesizer, which we can then play with in different ways, then it's a useful extra to have, and it's pretty straightforward to add in Pure Data. So we'll add it. I'm cutting that connection between the oscillator and the volume here, and I'm just going to put in the clip object just so you can hear it's an audio signal again, so it needs to have the tilde on the end. Let's just put it between between -0.5, can't type, and 0.5. And now if we listen, it's got buzzier ringing tone because it's added these extra harmonics. But we want some control over that. So as these you see with these boxes, they can have fixed parameters, but they also have inputs. So we will give ourselves a couple of extra sliders. We'll call this one, let's call it Waveshaping. It's not, and we'll give that a number. I like to do it this way around, 1.01. Instead of going from 0 to 1, I'll go from 1 to 0, because 1 is when we don't clip at all. So that's the 0, the minimal, the no clipping. And 0 is when we've clipped and clipped until we've squashed that wave to be almost nothing. So I like to put it on the right hand side of the slider. I also like to make it 1.01 just to make sure we can go to the full 1. So there's our wave shaping value. And so I'll add a number box there as well. And then this clip, the object, the input is for the minimum value and the maximum value. This is obviously coming into the maximum value, and of course we want the minimum the other side. So if the wave shaping for the maximum is 0.5, we want the minimum to be minus 0.5. The easy way to get that is to simply multiply this number by -1 and put that into the minimum. So if we see this now, our clipping starts off at 1 this end on the left, and as we go over to the right goes down to 0, and the minimum value starts at -1 and goes up to, or minus just 0. So let's now have a listen to that. Here's our tone, that kind of glassy effect, and now let's hear how the clipping, the wave shaping changes it. You hear that buzzing coming in as those extra harmonics appear. And you can hear that it still keeps its pitch, and we can take it out. We can keep doing it. We can keep adding it. It gets dirtier. It gets more and more harmonic. That wave is getting squashed. But of course, as we go to the end here, we've squashed it down to nothing. I mean, here at 0.1, for example, we've actually thrown away 90% of the wave. So although the sound got rich, we lost the volume, and that's a problem for us. So what are we going to do about that? What we're going to do about that is we are going to compensate by amplifying what came out of the clipped sound by what was lost. So as always, we add a new amplifier, which is a multiply on this audio route through the graph. And all we are going to do now is, so how much do we want to multiply this by? We don't want to multiply by a constant, and we don't want to have to set our own slider. We want to multiply by whatever compensates by what was lost in the wave shaping. So let's say we've clipped 0.5. The maximum of our waves is 0.5. So we need to multiply by 2 to get up back to our 1, assuming that the signal is between -1 and 1. So what we're multiplying by is the reciprocal of the clip value, the 1 over the clip value. If the clip value is 0.5, we multiply by 2. Or if the clip value, let's say, is 1 over 2, we multiply by 2 over 1. If the clip value is down to 0.33 or 1 over 3, we want to multiply by 3 over 1, by 3. So that's what we need. We need that value to figure out that value. And the fairly simple way to get that is to use the power. So to use power to the -1. So a power is like, I say, a number squared. Like 3 squared is 9, right? It's 3 times 3. You write it 3 with a little 2, or 3 to the power of 2, meaning we multiply 3 by itself 2 times. Or effectively, you multiply it by itself. There's 2 3's in that expression. If I do 3 to the 3, that's 3 times 3 times 3, which is 3 times 3 is 9, 3 times 9 is 27. So that's 3 cubed. We define, or mathematically, the power of -1 to the 3 to the power of -1 is 1 divided by 3, or n to the power of -1 is 1 divided by n. So that's what we're looking for here. So just to show you what that number is, if I have, when my wave shaping is 1, then, or just over 1, then you'll see that the power to the -1 is just under 1. If I take the wave shaping down to about half, then you'll see that the power to the -1 of that value is about 2. If I take it down to a fifth, or 0.2, then you'll see that the power to the -1 is 4.8, it's almost about 5. So that's what we want, right? We've taken it to a fifth of its value, and we're going to multiply it back by almost 5. And that will compensate for the volume that got lost. So let's put that output into our new amplifier. And so now you will hear, here is our sound with the wave shaping, our clean sound. Let's say the wave shaping is nothing. Now as I increase the wave shaping, you'll hear it become more buzzy and more harmonically rich, but actually it won't start getting quieter. It will even sound a little bit louder, because psychologically those distorted sounds sound louder. And in fact, I think even the real volume is louder. So it's getting very rich and interesting now, but it's not losing its volume. Now we've got that real distorted sound coming through. It's very distorted, but it hasn't lost the information of the pitch. It hasn't lost the qualities, the FM qualities that we had. We've still got all of that richness and complexity in our sound wave. So we can now go on and use that. Okay, I think I'm leaving this video here, and I'll see you soon.